In this video, I want to introduce you to exponential and logarithmic functions. Exponential functions, I think we've heard of these in a number of situations probably in the past. One major area is exponential growth, which of course we've probably seen this graph at some point in our lives, whether it's a sociology or history class. Population has been growing exponentially throughout the world, and it does it regionally sometimes as well. It just means at the very beginning of time, things start off at a very, very slow growth rate, and then as time progresses, it increases faster and faster, not just a linear rate. A linear, remember, being a straight line. We don't see that. We see a much faster growth rate with time. It doesn't have to be just population. Money, it's another common example. You guys may have seen compounded growth, compounded money before. Those are just exponential growth patterns. Not just going to be those. We're going to see a number of examples in this chapter. Could be disease rates, could be bacteria, could be any number of things. But anytime really you see percentage growth is just talking about an exponential function, exponential growth. Or if you see doubling, tripling, halving, quartering, any of those keywords, that's talking about exponential growth. Let's start by looking at exponential functions. So first, let me write out the generic equation. F of x equals b to the x. So now you might be saying this just looks like our quadratics. We have an exponent. Difference is the base is set. It's a number. X obviously is the variable. So the variable is now in the exponent and not in the base. Now a couple restrictions to this. B, the base, cannot be equal to 1. Because if we add 1 raised to any power, it's just 1, so that's not growing exponentially. B also has to be greater than 0. So if b is equal to 0, that's not possible to be an exponential function because 0 to any power is still 0. But also if it's negative, what we would notice is it alternates between positive, negative, imaginary, and real. So we do have these two restrictions on our b, one that it can't be equal to 1, and 2 that's strictly greater than 0. So if we take just some basic ones, 3 to the x, that would be an exponential function. 1/5 to the x, that would be an exponential function. Then we could evaluate these pretty easily. If I go back to the f of x being equal to 3 to the x, and just ignoring this one for right now, if we were to say take f of 2, that means we're plugging 2 into the exponent. We'd have 3 squared, which is equal to 9. Again, this is looking quadratic because I chose 2 as my exponent, but the difference is if I go back to my original function, I can plug in any number for that exponent. That is the number that's changing, so it's 3 to the 5th, 243. So that's the number that can change. What we'll see in a different video is that it does set up that exponential growth pattern, that first figure I showed you, where it could be growth, could also be decay. That 1/5 that I'd written up a second ago, that would actually be a decaying function that is decreasing in size, so it would be going the opposite way around, be decreasing. Before we get there, let's look at logarithmic functions. What we've seen, especially back in chapter 1, inverse functions, every function has to have an inverse, has to have something that can undo it. And so for exponential functions, the inverse of those, logarithmic functions. So let's go back to that initial function notation, f of x. But I'm going to just call it y this time. Y is equal to b to the x. That's my exponential form. I want to convert this over to logarithmic form. I want to view what this thing would look like in log form. So what a logarithm does is it solves for that exponent. The log is always equal to the exponent. So that would be the logarithmic form, same exact equation, just in log form. So anytime I have that exponential form, there's plenty of times where I might want to know, well, what exponent gives me a value y? So for instance, if I just take a simple one, let's take 8 is equal to 2 to the x. What x value would make that true? Well, it's pretty intuitive to see in this case. It's just 3. But what if it's not that simple? What if it's something like 1.5 equals 2 to the x? Well, that one I don't really know off the top of my head, so we're going to have to use a logarithm to solve that. So to convert things to logarithmic form, what we see, the base b, the number that is being raised to a power before, that has become a little exponent in my, sorry, not an exponent, but a subscript in my logarithmic form. It's read log base b of y equals x. That b is written small and kind of underneath of the log, almost smaller than everything else and beneath it. The x, the exponent, has moved to its own side because we're trying to solve for that x. And then what the exponential was equal to has moved to what we're taking the log of, log base b of y equals x. So if we just take a couple examples converting between the two, let's say we have 3 to the x is equal to, let's say, 8. Not saying I want to solve it, just convert it over to logarithmic form so that we can solve it. That would be log, my base was 3, 8 equals my exponent x. Let's take, call it y to the third power is equal to, let's go x plus 1. So this one, we actually don't have quite an exponential because the 3 is known, but we could convert this over to logarithmic form as well. This would be log of y, log base y, of x plus 1. That is a y, not a 4. Notice that x plus 1, because I have more than one thing inside that logarithm, I've placed it inside parentheses. And then the exponent is what I've set it equal to. We can go backwards very easily. So let's say we want to convert from logarithmic to exponential form. Let's take log base 7. X is equal to 4. Maybe I want to solve this. What would that look like in terms of exponential form? That would be 7 to the 4th is equal to x. Now you can see to solve that thing for x, we just have to raise 7 to the 4th. Let's take log of b, and we'll say 3 equals 7. So we're going to convert this over. Our base is b, our exponent is 7, and the value is 3. And this, again, we could solve. We would just take the 7 through to both sides, and we would find out what b is equal to. Hopefully this gives you an idea of how to set up our exponentials and logs in terms of one another, and gives you a general idea of what they're doing.